Hello friends and welcome to this video. We are with the sixth chapter of the subject Advanced Digital Signal Processing, and the chapter is titled Adaptive Filters. We are already covered with the first two topics. The first topic that it was adaptive filtering system identification, and the second topic that it has followed the FIR adaptive filters. Now we are going to have continuation of the discussion for design of the FIR adaptive filters with the current topic that it is titled as the steepest descent adaptive filters. So as we recall the first topic that it was adaptive filtering system identification. Before beginning the exact system identification and the details of adaptive filtering, thereupon we had a discussion with respect to the design of Wiener filter that we have seen in the previous chapter. The previous chapter that it was the linear prediction and optimum linear filters. So thereupon we recalled the Wiener-Hopf equations, and as we are in the domain of adaptive filters here, a modification with respect to the consideration of non-stationary aspects. The same example was continued for the adaptive type of the filtering, and at the end the very important three rules what we can call to be the algorithm, that is the adaptive filter should be having the set of the rules here, three rules we have seen thereupon. Next to that, in the second topic, thereupon we have discussed a direct form FIR adaptive filter. Now in continuation to all the discussion with the help of the mathematical equations, I will like to recall that in the designing of an finite impulse response, that means FIR adaptive filter, the goal, the ultimate aim is to determine the vector W suffix n at the time n that minimizes the quadratic function given by eta of n, that is equal to the estimate of, that is represented capital E of inside the curly brackets mod square of small e of n. So for minimization purpose, one way is that the setting of the derivatives of the LHS representation here zeta of n with respect to the conjugate of W of k equal to 0. But another approach is also there, that is to search for the solution using the method of the steepest descent, and that it is our current topic here. Now the method of steepest descent is basically an iterative type of the methodology or procedure, you can say, that the basic idea, the particular procedure. So let us consider here that W suffix n will be an estimate of the vector that minimizes the mean square error denoted by zeta of n at the time small n. Now at the time n plus 1, a new estimate is formed by adding a correction to this W suffix n that is designed to bring W suffix n closer to the desired solution. Now the correlation here involves taking a step size that is represented by mu in the direction of the maximum descent down the quadratic error surface. So for example, let us discuss that there it is a three-dimensional plot of a quadratic function of the two real valued coefficients denoted by the W of 0 and W of 1 here. So here we have the quadratic function of the two weights shown with the help of the three-dimensional plot here, and below that here we have the mathematical representation of zeta of n in terms of W of 0 and W of 1 here. So zeta of n is equal to 6 minus 6 times W of 0 minus 4 times W of 1 added by 6 times the addition of squares of W of 0 and W of 1, finally added by 6 times the multiplication of W of 0 with W of 1. Now here if we talk about the boundaries or the counters of the constant error that we are focusing on, when it is projected onto the W of 0 and W of 1 plane, so it will be forming a set of concentric ellipse here, that we are going to show with the help of again the illustrative form here. Now the direction of the steepest descent at any point in the plane is the direction that a marble would take if it were placed on inside of this quadratic bowl, and mathematically this direction is given by the gradient, and this gradient is a vector of the partial derivatives of the zeta of n with respect to the coefficients w of k. For the quadratic function into the previous equation, the gradient vector can be represented here. So for gradient, we have the use of symbol delta here. This is basically the vector spatial del operator, and with this particular notation we are not having any kind of dot or the cross sign with the operand here. So here we have del zeta of n. So as this is the gradient, it is basically a ratio here. So into a matrix form, a column matrix having only the two rows, a single column here, we have the first element denoted by the partial differential. So partial differential del w of 0 for zeta of n, and the second element is del w of 1 of zeta of n. Here we can represent it as the first element with respect to the earlier mathematical equation. We have it 12 times w of 0 added by 6 times w of 1 minus 6, whereas the second element, that means the second row element, it will be 12 times w of 1 added by 6 times w of 0 minus 4. So as we had already discussed the elliptical form for the counters here. So for any vector that in general represented by W, the gradient is orthogonal to the line that is tangent to this elliptical path or the counter of the constant error at W shown with the earlier illustration here. But since the gradient vector points in the direction of the steepest ascent here, the direction of steepest descent points in the negative gradient direction is there. So therefore, whatever the update equations we have for W of n, here we denote it by W of n plus 1, that is equal to W of n minus mu times delta zeta of n. So here the step size mu is affecting the rate at which the weight vector moves down the quadratic surface and must be a positive number. So if there it is a negative value for the mu, which would move the weight vector up to the quadratic surface in the direction of the maximum ascent and would result into the increase into the error. Now if it is any very small value of the mu, the correction to w suffix n vector is of course a small one, and the movement down the quadratic surface is very slow, and as mu is increased further, the rate of descent will increase. However, there is an upper limit on how large the step size may be, and for values of mu that exceeds this particular limit set by us, the trajectory of w suffix n becomes unstable and unbounded as well here. So now here we have the steepest descent algorithm that can be summarized with the help of the following steps here. We are going to discuss with the four steps here one by one. So let us have the first step here, that is to initialize the steepest descent algorithm with the initial estimate that can be denoted w suffix 0 here. So 0 for the initial case here, and this is for the optimum weight vector w here. Now the second step is to evaluate the gradient as we have shown with the help of the mathematical equation on the previous slide. This gradient will be of zeta of n at the current estimate of w suffix n for the optimum weight vector here. This will be the second step, and in the third step we have to update the estimate at the time small n by adding a correction that is formed by taking a step of size mu in the negative gradient direction here. So here we denote w suffix n plus 1 equal to w suffix n minus mu times delta of zeta of n. And the fourth and the last step will be to go back to the step number 2 and repeat the complete process that we have seen up till now. So these are the very important steps for the current topic, that it is the steepest descent algorithm here. Now we will add certain more information with respect to this particular topic here. So let us evaluate the gradient vector that we have denoted by delta of zeta of n. So here the assumption can be made there that the vector w is of the type complex here, and the gradient is the derivative of the estimate e of mod square of small e of n that we have from the block schematic we have learned into the first topic of the chapter, and this will be with respect to the conjugate of w here. So therefore we have delta zeta of n is equal to delta estimate of mod square of e of n if we substitute it. So by the next step we can also represent it to have, first of all, the estimate of, inside there it is the gradient of, so delta in multiplication, not exactly the multiplication there, it should not be any symbol there, so delta mod square e of n here. And we can also apply it to the conjugate form only, so here we can write estimate of e of n multiplied by here delta conjugate of e of n here. And as we have delta conjugate of e of n to be represented as minus conjugate of x of n being the input discrete time random process here, so it will follow that the gradient zeta of n will be equal to minus of the estimate of e of n multiplied by conjugate of the discrete time random process x of n here. So therefore, if we have a consideration of step size represented by mu, the steepest descent algorithm will take the form w suffix n plus 1 is equal to w suffix n added by mu times the estimate of e of n multiplied to the complex conjugate of x of n. Now, in order to check the steepest descent algorithm having the update equation for w suffix n here, let us have the consideration that the case is of the stationary process, and where the representations, the usual notations, x of n for the input discrete time random process and the desired signal denoted by d of n. So x of n and d of n, if they are jointly wide range stationary random processes, so that time mathematically we can represent that capital E of the multiplication E of n with the complex conjugate of x of n will be equal to the estimate of d of n into conjugate of x of n minus the estimate of w suffix n transpose multiplied by x of n with the complex conjugate of x of n. So simply we can denote it with the help of the statistical matrix r suffix dx in the small casing here minus capital R suffix x into the vector of weights w suffix n. The meaning of the symbolic notations are the same that we started with the first topic of this particular chapter. So therefore the steepest descent algorithm for this current case will become represented by w suffix n plus 1 is equal to w suffix n added by mu times the subtraction, where it is r suffix dx minus capital R suffix x into w suffix n here. So here if w suffix n is the solution to the Wiener-Hopf equations, w suffix n can be described as the inverse of capital R suffix x multiplied by the cross correlation between the desired signal and the input discrete time random process. So there it is small r suffix dx. So therefore the correction term will be equal to 0 and w suffix n plus 1 will be equal to w suffix n for all the values of small n here. Now it will be quite of greater interest that how the weights evolve in time, beginning with the arbitrary initial weight vector denoted by w suffix 0. So here one helpful property here we have the definition of the same can be given here. So we can regard this to be the property one here, and this is for the joint wide sense stationary processes as earlier discussed, the desired signal t of n and the discrete time input signal x of n here. So the steepest descent adaptive filter will converge to the solution of the Wiener-Hopf equations. So here we denote it as limit n tends to infinity for w suffix n, that is equal to the inverse of capital R suffix x into small r suffix dx. So if the step size will satisfy the condition here it is provided that the mu is greater than 0 but it is less than 2 divided by lambda suffix max here, where this lambda suffix max is the maximum eigenvalue of the autocorrelation matrix denoted by capital R suffix x. So here we have discussed the very important steps of the steepest descent algorithm. So in short, we can say the steepest descent adaptive filter procedure we have seen here, and the very important property is also addressed here. So here we can conclude the current topic, and we shall continue into the same chapter with the next lecture for the topic titled the LMS algorithm. Thank you.